3 of 3 on our 10.2 notes. Moving on to the last part, properties of gases, starting with the kinetic molecular theory. So as review, this states that gas particles move in constant, rapid, random, straight line motion. So we assume there are no attractive forces between gas particles, so not even LDFs, that's what we're assuming. We're saying that collisions between the particles are completely elastic, so all the energy is transferred, and that these particles occupy negligible volume. So those are all of the assumptions of the kinetic molecular theory. Gas samples that behave according to these assumptions are called ideal gases, and no real gases are completely ideal, but these assumptions actually allow us to do a lot of really good approximations. So of course we use the ideal gas law to do those approximations. The units for this are actually pretty specific depending on whichever R you're using. So the R I'm going to use, so R is the ideal gas constant. And that ideal gas constant is 0.0821 atmospheres times liters over moles times Kelvin. So the idea is that you're going to want to cancel out all of the units that you don't want to end up with at the end. So you want to make sure all of the units of everything else match these units. Now there are other R's, and you can look at those on the back of your periodic table. You can really use any one you like, just make sure that your units cancel. So for the purposes of the rest of these problems, I'm going to define my variables with these units. So P is pressure, and that's going to be in atmospheres. So again, atmospheres, I want that to match. N is always number of moles, just abbreviated mole. The T is temperature, and temperature is going to always be in kelvins, and V is our volume in liters. Alright, example 4, consider the following samples of gas. So container A and container B are both at 600 torr and 40 degrees Celsius. The only difference is the first one's helium and the second is sulfur dioxide. So this says to find the density of the gas in each container. Now our ideal gas law doesn't have directly a density calculation, but if we do some substitutions and just a little bit of derivation, we can actually figure out the density, and it's a pretty interesting way to do it. So if we're going to start with our equations, we're going to start with PV equals nRT, our ideal gas law, and molar mass. So molar mass, I'm going to write as capital M, that's molar mass, and that's going to be equal to grams per mole, so M over N, mass per mole. So we're going to start with those and we're going to combine them. The first step that I'm going to do, and I'm just going to write my steps over here, so when you're looking back at this later, you can refer to that. So substitute first. Mass over molar mass for N, because grams over grams per mole just leaves you in moles. So that is N. So writing that out, we get PV equals M over big M times RT. Okay, next step, we're just going to rearrange this. Molar mass, getting that by itself, equals mass times RT over PV. And now is where density comes in. So if we remember, density equals mass over volume. So since D equals M over V, we can now substitute in our equation. And we get molar mass is equal to, well, if D is equal to M over V, we can just have D right on the top, D RT over P, over our pressure. So our mass over volume became our density. Okay, next up I'm going to rearrange to get density by itself. So density equals molar mass times pressure over our ideal gas constant times temperature. And this is going to be our useful equation that we're going to use to find the density of these gases. So first one, container A. So for container A, I'm just going to label this D sub A for density of A. molar mass times its pressure over the ideal gas constant times temperature. So I'm going to need to calculate my pressure here. It's in torr, so I'm going to need to put that in atmospheres. So if you look on the back of your periodic table, you'll see the conversion factors. So 600 torr is equal to 1 atmosphere over 760 torr. And that's going to give us 0.78947 atmospheres. And 40 degrees Celsius, 40 plus 273, is going to give us 313 Kelvin. So that's our pressure, that's our temperature. We're going to need to plug those in here. Okay, so our molar mass of helium, just look at the periodic table for that one. So you get 4.026 grams times inverse moles, same thing's grams per mole, times your pressure, which we calculated up here. We just turned it into atmospheres, so 0.78947 atmospheres over our ideal gas constant, 0.0821 atmospheres times liters times inverse moles times inverse kelvins times our T for temperature, which is 313 kelvins. All right, going through and canceling out all our units. This is always a good step to do to make sure that you've got everything in the right units, and that way your numbers aren't wrong when you calculate this out. So kelvins go away, atmospheres cancel out, inverse moles cancel inverse moles. Great. All right, we're set. So we are in, let's see, grams per liter, which is what we want for our density. So when you type all this into your calculator, your density is 0.1 grams per liter. So that's the density of the gas A, or your helium in container A. Now let's go ahead and do container B in the same exact way. Right now would be a very good time to pause the video, and just like we did for container A, go ahead and do container B, and then come back and check your work. Okay, hopefully you were able to get the density for container B, so let's review. So the density in B, we're just going to plug in our molar mass that we looked up from the periodic table and add it all together. So it's 4.07 grams per mole. Same pressure. Over same R. And same temperature. So again, the only thing that changed here is our molar mass. When you plug all this in, oops, that's kind of big, you end up getting 2 grams per liter. Huge difference. Okay, part B. Find the average root mean square velocity of the gases in each container. So at the same temperature, molecules have the same average kinetic energy that's not dependent on their size. It only is dependent on temperature. But lighter molecules actually are moving at a faster speed. That does depend on their size. So at the same temperature, molecules have the same average kinetic energy, and the formula for that is Ke equals 3 halves RT, but lighter molecules have a faster speed. And that is kinetic energy is equal to 1/2 mass times velocity squared. And for a molar sample, we can say that the mass is equal to the molar mass, because in 1 mole, it's a molar sample, so it's going to be, they're going to be equivalent. Okay, so find the average or RMS velocity of the gases in each container. The first thing we need to do is set these equations equal to one another. So we need to use both equations here. So set equal. So our kinetic energy is equal to 1/2 mv squared, which is equal to 3/2 RT. And then I'm going to replace my mass with molar mass because we're looking at molar samples. So 1/2 molar mass V squared equals 3/2 RT. And then rearranging all of this, V is going to be equal to the square root of 3 RT over molar mass. And for here, our R, we're going to define our R, is 8.314 joules times inverse moles times inverse kelvins. And one little note here that we're going to need to do is for later, when you're doing this, molar mass should be in kilograms per mole, because we're going to need to cancel something out with it later. So in kilograms per mole, not grams per mole. So all you need to do is divide by 1,000. Okay, so let's figure these out. Now that we have our equations, let's find the root mean square velocity for container A. So for container A, the velocity of A is equal to the square root of 3 times our R, 8.314 joules times inverse moles times inverse kelvins, times our temperature, which was the same we calculated above, way up here, 313 Kelvin, divided by, now this was helium, remember, container A was helium, and its molar mass was 4.026. So when we plug it in now in kilograms, make sure it's in kilograms because we're going to need to cancel something in just a second. We end up getting 4.026 times 10 to the negative third kilograms per mole. Okay, so canceling everything out, we cancel out our moles, our inverse moles cancel, our kelvins cancel. Now joules, the units of joules are kilograms times meter squared times inverse seconds. So these actually end up canceling out. So our kilograms end up canceling out our kilograms here. And then you have meter squared over inverse second squared. Take the square root of that and you end up in meters per second. So your answer ends up being 1390 meters per second. Okay, so that's container A. Let's do container B. At this point, please go ahead and pause the video and see if you can figure out the velocity for sulfur dioxide in container B. Okay, hopefully you were able to plug that in. So the velocity for container B, we're going to set this up exactly the same way. 3 times 8.314 joules times inverse moles times inverse kelvins. Same temperature. The only thing that changes is our molar mass at the bottom, 64.07 grams per mole. But if we do times 10 to the negative 3, now we're in kilograms. Times inverse moles. And again, canceling everything out. Moles cancel, kelvins cancel, your kilograms cancel, the kilograms and the joules, you're left in meters squared per second squared. Take the square root of that and you end up in meters per second. So 349 meters per second. So we can see that helium is much smaller and it's going much, much faster than our sulfur dioxide. Okay, part C. Each container has 0.5 moles of the gas, half a mole of the gas. The volume of container A was 16.07 liters. Well, the volume of container B was 15.96 liters. So what is the difference here? They should be the same. So according to the ideal gas law, that says all these crazy assumptions, well, not crazy, all these assumptions, these should be equivalent. So both containers have the same moles of gas at the same temperature, so they should occupy the same volume. So just to do a calculation to see what it should be, PV equals nRT, rearrange that to get velocity, just like we solved for up here. So our velocity equals nRT over P. Plugging everything in, we said it was a 0.5 mole sample. 0.0821 is my R. And we're at 313 kelvins over our pressure, which we calculated above, is the same, 0.078947 atmospheres. And if you calculate all of this, this should give you 16.27 liters. Now it says that the volumes in real life were 16.07 liters, that's smaller, and 15.96 liters, much smaller. So container A is an ideal gas, helium, a little less off than sulfur dioxide, which is much bigger. So explain the difference. I want you to please pause the video and think about why that difference is the way it is, and then come back. All right, so it turns out that the reason lies in the intermolecular forces. So real gases do have small intermolecular forces. They are not ideal, and they do have attractive forces. Substances with stronger intermolecular forces deviate more. So the one with the stronger intermolecular forces is going to be sulfur dioxide. So we can tell in a couple of ways. So sulfur dioxide, it takes up less room than the helium does, and we can tell by looking at the structure of it. So sulfur dioxide is much bigger, and so its electron cloud is going to be a lot more polarizable. It's going to have stronger intermolecular forces than helium does as a noble gas. So real gases, meaning not ideal, have small intermolecular forces. So they're still there. They're not negligible. They're still there. They're just much smaller than in a liquid or a solid. And they deviate from ideal because of that. Substances with stronger substances with stronger intermolecular forces deviate more. So gas B has more / stronger intermolecular forces. All right, last page of our notes here. The van der Waals equation. So the van der Waals equation, you don't need to memorize this, and you don't need to do any calculations involving this on the AP test. So this is the equation, and you can see there's part of the ideal gas law in there. So what it says is that P is the observed pressure of the sample, V is the volume of the container, A is some parameter, like a fudge factor, related to the attraction between particles, and B is a parameter related to the volume per particle. And you don't need to know where those come from or how those work. But I would like you to take a second and please examine the graph and figure out the answer to these 2 bullet points. Under what conditions, so what temperatures, high or low, and what pressures, high or low, will a gas behave more like an ideal gas? And here's the line for the ideal gas. And which kind of gases are the most ideal? Are they strong IMFs, weak IMFs, large size, or small size? Pause the video and then come back. Alright, so according to the graph, when you have conditions of pressure that are low and temperatures that are high, your gases are going to behave more ideally. So low pressure and high temperature. And what kinds of gases are the most ideal? Well, the smaller ones are more ideal. So, small size. And you also need to take into account their intermolecular forces. With weak IMFs. Okay, so that is everything that you need to know about gases, and that is the end of your 10.2 notes, the end of video 3 of 3.